Alright, today we're going to be solving this problem if A, B, and C are sets. Prove that A intersect B union C is equal to A intersect B union A intersect C. Okay, so there's a few definitions we're going to need to recall here. So first, we need to recall the definition of a set inequality. So let's let E and F be sets. Then if I say that E is a set which is contained in F, this is the same thing as saying if X is in E, if I take some element of E, then it must be an element of F. Okay? And then, second definition, we will say that two sets are equal, E is equal to F, if we have both sides of this set theoretic conclusion, i.e. if E is contained in F and F is contained in, and F is contained in E. All right. And then finally, we need the definition of the intersection and the union. Okay. So X is going to be within the intersection E intersect F, if and only if X is in E and X is in F. So recall, if I have the set E and the set F, their intersection is the set the set whose elements belong to both E and F. And then recall also that X is in the union if X is in E or X is in F. Here our picture is the set whose elements are contained in either E or F. Okay, so the intersection sign is symbolizes an AND symbol, and the union symbol can be replaced with this OR symbol. Okay, with these definitions in our hands, let's go ahead and tackle this problem. So remember, to show that two sets are equal, I need to show both sides of the set theoretic conclusion. So let's start by proving this direction. So I'm going to prove that this set is contained in the set on the right. To do that, I need to start with an arbitrary element. So let X be an arbitrary element of A intersect B union C. And then to show this inclusion, I just need to show that X belongs to this set automatically. Okay? So let's unpack what this means. So this tells us that X is in A and X is in B union C. That's the definition of the intersection. Okay, so this tells me that X is in A no matter what, and then X is either in B or X is in C. All right? And so then this tells me that if X is in A and it's either in B or C, then X must be in A and B, or X must be in A and C. There's two possibilities here. So if X is in B, then X is in A intersect B, so it's in A and B. And if X is in C, then X is in A intersect C. Okay, so if X is in C, then X is in A and C. And then what this information tells me is that in either of these cases, I know that X belongs to A intersect B or A intersect C. Okay, so this is the first inequality. Now let's tackle the other. The other direction is similar. Well, not similar, but I'm going to similar proof strategy where I start with an element of this set and I try to show that it must be the set on the left-hand side. So we're going to let X be an arbitrary element of A intersect B union A intersect C. So this tells me that X is in A intersect B or X is in A intersect C. Okay? So in either of these two cases, X belongs to A by definition. Okay? So I guess we could unpack this a little bit more. X is in A and B, X is in B, or X is in A and X is in C, again by the definition of the intersection symbol. So now, in either of these cases, X is in A, no matter what, and then in case 1 I have X is in B, in case 2 I have X is in C. So this means that I know X is in A, and I know that X is in B or C. And finally, if I replace these ands and or symbols with set intersections and unions, this is telling me that X is in A intersect B union C. Okay, so since we've proven both directions of the inequality, we've proven this set theoretic inequality.